This is part 3. In part 3, we are going to look at error analysis, which I've coined E2. E2 is Taylor's formula with remainder. Another name for this theorem, which sometimes shows up in AP, is Lagrange error bound. So I may refer to either one of those. Short would be E2. So in this particular error analysis formula, Lagrange tells us that the error is not bounded, but equal to some expression here. The key to this is that it says for some number c between a, the center, and x naught, some given value of x, to be discussed further in detail later. But the point is, we don't know what c is. We'll never know what c is. So we're going to analyze some error using this Taylor's formula or Lagrange error bound. So let's take a look at number 6 from the notes. In number 6, it wants to use the first two non-zero terms of a Maclaurin series to approximate the sign of x. Estimate the maximum error if x is between -1 and 1. First, let's analyze this error using E1. So using E1, we would say that the sign of x is approximately x minus x cubed over 3 factorial. And then we would continue by saying the magnitude of error, which is going to be less than or equal to the first omitted term, x to the 5th over 5 factorial in magnitude. Can we say this though? Can we actually make this assertion? We would have to ensure that the series for sign of x is always strictly alternating and decreasing in absolute value to 0. It had to be true for all values of x. Well, let's kind of investigate this. Would it be true for x equals 1, 1 minus 1 over 3 factorial? We certainly see that this would continue to strictly alternate and decrease in absolute value to 0. But how about the sign of -1? Well, the first term then becomes negative, but the negative in the second term will be canceled out with the minus in front, so it's plus 1 over 3 factorial minus 1 over 5 factorial plus ... So no matter what value of x that you choose, the series will always strictly alternate and decrease in absolute value to 0. So we can in fact use E1 and say that the error is less than or equal to the first omitted term. So now we want to know what is the biggest possible error for the range x between -1 and 1. Well, we certainly know that this quantity here will be largest when x is equal to 1. 1 to the 5th over 5 factorial, which is 1 over 120. So the maximum error is 120 using E1. Now, let's continue. We're going to look at E2, the new theorem. Okay, so here is what Lagrange says. We're going to say the sign of x is approximately x minus x cubed over 3 factorial, so that starts off the same. Let's figure out what polynomial this is. We certainly can see that this is a third order polynomial, but the fourth order polynomial simply adds a 0. So this is also the fourth order polynomial. And it is important to maximize the order, so we're going to push it out to 4. So let's see what Lagrange says. Notice that this is centered at 0. So Lagrange says the error, which is equal to the remainder following the fourth degree polynomial or fourth order polynomial. So R4 of x is actually equal to the fifth derivative. We have to take one more than this value here, says the theorem. 1, 2, 3, 4, 5 derivatives at some number c, x centered at 0 to the power of 5 over 5 factorial. We do not know what c is. We do not know what c is at all. But the only thing is that c must be between the center, which is 0, and any value of x, which is between -1 and 1. So this leads us to c being between -1 and 1. All right, so we have to figure out now, here's kind of the key to this, fifth prime at c. Well, the first derivative of sine would be cosine. The second derivative would be negative sine, then negative cosine, then back to sine. One more derivative would bring us to the cosine of c. So this expression here is equal to the cosine of c, x to the power of 5 over 5 factorial. Again, one more time, we don't know what c is, but we do know that the cosine of c can be bounded. We know at the biggest, cosine of c can be less than or equal to 1. So this expression is 1 x to the 5th over 5 factorial in magnitude. Now we go back to saying that x is between -1 and 1. So the biggest amount of error that this could be is when x is equal to 1, so it's less than 1 over 5 factorial, which equals 1 over 120. The same answer, the same bound that we got using E1. That won't always be the case, but it is the case here. You may think to yourself, geez, this E2 seems much more complicated. And to some degree, yes, it is much more complicated. And I would certainly use E1 if it's strictly alternating. But if it is not strictly alternating, then I'm forced to analyze the error using E2. Now let's move on to 8a. And in 8a, it wants to approximate the square root of 1 plus x using two terms. And we want to estimate the error when x is between -0.01 and positive 0.01. We cannot use E1 here. This series is not strictly alternating. So we are forced to use E2. So let's take a look. We're going to say the square root of 1 plus x is approximately 1 plus x over 2. You might notice that this is simply a linear approximation. This is a polynomial of order 1. Now for error, we say that the error is equal to R1 of x, which is equal to f, now we have to say double prime at c, x also centered at 0 to the power of 2 over 2 factorial. Can you guess what we need to do next? Besides saying what c is bounded to, c is between -0.01 and positive. But what do we do next at this point? If you're saying to yourself, I know I need to find the second derivative of f at c, then you are correct. The first derivative, the radical 1 plus x, the first derivative is going to be 1/2 1 plus x to the -1/2. If I find the second derivative, the thing we really want, then that's going to be -1/4 1 plus x to the -3/2. So we're going to continue our equality here. So f double prime at c is going to be, we're going to put in the absolute value, so I'm going to get rid of the negative. 1/4 1 plus c to the power of 3 halves, x squared over 2 factorial. We're still in the equals statement. The question now becomes, if I want to bound this, I want to find what the maximum value of this is, then I've got to figure out what value of c will in fact make that maximum. Analyze it for a second. You probably realize that the value will be max when c is negative 0.01. That makes this then less than 1 over 4, 1 minus 0.01 to the power of 3 halves, x squared over 2 factorial. Now I've gotten rid of the absolute value because everything is positive, including x, because it's squared. Then I'm going to figure what this is, and that is going to be approximately 0.2538. Again, x squared over 2 factorial. So there's our expression. Now we go back to x and say, well, what is the value of x that will make this expression maxed? And we're going to say that's going to be when x is equal to plus or minus 0.01. So 0.2538, 0.01 squared over 2 factorial, which is approximately 0.0000. That's 4 zeros after the decimal place. 1, 4. I rounded this up just slightly to guarantee that this is a ceiling. The error cannot go beyond this value. So that's E2. One of the kind of tricky things about E2 will be addressed in question 8b, where we kind of take a look at C and analyze that a little bit further. So here's 8b. Use the linearization, the first order polynomial above, to approximate the square root of 1.5, or said differently, 1 plus 0.5. Important to note here, the center will say a equals 0, and x naught, see that's what makes this a little bit different. We have an x naught. X naught is 0.5. That's our value of x, whereas the other one gave us a range for x. Okay, so we're going to say that the square root of 1.5 is approximately 1 plus 0.5 over 2. We just plug that into the linear approximation. And that's equal to 1.25. Now let's take a look at the error. The error in magnitude is equal to, if you recall, we took the second derivative at c, so that's 1 over 4, 1 plus c to the 3 halves, x, but here we have an x, our x is 0.5 squared over 2 factorial. So with an x naught, we don't use x in this expression, we actually plug in our x naught value. Here's the key now. C has to be an element of a to x naught. You can't exceed x naught. So this expression here gets bounded differently because c cannot exceed 0.5, nor can it go below 0. So the expression will be largest when c equals 0, so this is going to be less than 1 over 4 times 1 to the 3/2, 0.5 squared over 2 factorial. And you could see that that's equal to 1 over 4 times, well, 1/2 squared is 1 over 4, all over 2, so that's going to be equal to 1 over 32. So the maximum error for approximating the square root of 1.5 using the linear approximation, our maximum error according to the Lagrange error bound theorem is 1 over 32. I'm going to stop the video here, and I'm going to ask that you work from the notes packet on number 7, 9, and 10. That will be your homework assignment from the notes packet, number 7, 9, and 10.